Hi everyone. In this video, let's discuss about working with imbalanced data. Now, what do I mean by imbalanced data? Where, as the name suggests, when the data is not balanced for your machine learning purposes. For example, if you are looking at failure analysis and you have like, okay, I turned the switch on and the light came up, right? I mean, look at the room temperature and other metrics that go along with it. But one day the light fails. Now you want to understand why did the light fail, right? So maybe it has to do with the conditions in the room and your voltage fluctuations. I don't know. There are many parameters, right? But the failure happens very rarely and the success happens quite a bit. So if that doesn't make sense, if you're studying, for example, cancer data, you probably have a lot of information about healthy, or non-cancer related data sets, data points, but then cancer related data points, you may not have as many, which is a good thing. We don't want to see a lot of cancer data, but if you're trying to address or understand why something is happening, you need to have enough information. So whenever you're trying to do these type of binary classifications, you may end up with one class that's often important to you. The reason why you're studying this whole thing is because of that one class, right? So you may not have enough data. So how do we augment it? Now, there are many videos on YouTube about this imbalance, so I don't want to use a standard data set because the whole point of my tutorials is image processing. So let's actually focus on an image to understand what imbalance means and how do we handle it. So first of all, the image I'm going to use to explain is an image, something that looks like this. Again, it's collected on a X-ray microscope, which is like micro CT, but better. And this is a 3D volume. I'm just showing you one single slice. So if you look at this, I mean, it's very easy to segment, these dark regions. Well, let's not get into how easy or difficult, but let's see how much area you have of each. If you look at this, in fact, let's go ahead and look at the histogram. It's not that clear, but you can see one peak down here, one peak up here, right? So these two correspond to one. The dark one corresponds to the dark pixels, and this one corresponds to most of these gray pixels, and there is a small hump here which corresponds to this bright region. So we have a lot of this, but then in addition to this, I also would like to analyze this region. I hope you guys can see this. Let me draw a box around it. For example, this region. Okay, that has some texture, but then the grayscale matches the grayscale of this other region. Okay, but this is why we need machine learning, whether it is traditional or deep learning, to segment these type of things that leverages texture. Deep learning or machine learning can definitely help us. Now, but that I don't have a lot of that region, and it makes it a bit difficult to segment this. Now, the bright region also, I don't have a lot, but this is very easy to segment. So this is what you don't get when you look at typical data sets in an Excel form, and then you try to see how to handle imbalanced data. Visually, you can see that, okay, the bright pixels, you don't have much of it. That doesn't mean it's difficult to segment it. This, we don't have much of it, and it is difficult to segment. So let's look at the corresponding labeled image, and here is the corresponding labeled image. If I hover my mouse over this region, you can see it gives a value of 201. That means the label 201 in our image is the one that's challenging to segment. Now the bright regions, let me move this so I can identify, have a value of 65. So we don't have a lot of bright region, but my suspicion is it's easy to segment that. And the other two regions with values of 33 and 231, we have enough of it. Okay, this is the problem. This is our imbalance problem. Two classes imbalanced. Going back to image, the bright region is imbalanced. We have very low of it. And this textured region is imbalanced. Again, we have very low of it. Now let's get into the coding part and how to address this. Now, before actually getting into coding part, let me address the top 7 ways or techniques to actually address this. Now, actually, I should have made it top 8, but I don't like the number 8. So let me call it the 0th technique. The 0th technique is collect more data. If you have a way to get more data, that's always the best way to do it. Otherwise, everything else you do is a trick. Okay, so collect more data is your technique number 0. If you have a way to do that, go ahead and do it. Now, technique number 1, if you have a choice of picking, well, you do, the approach, I recommend decision tree based approaches rather than logistic regression or support vector machines, or even deep learning. I mean, with the decision tree where you can engineer your features, these things work very well. Decision trees are designed to work with this type of imbalanced data. The only thing is you may have to worry about overfitting your data. Okay, so how generalized is that model? Can you apply that model to other data sets that look very similar? This is one potential side effect. I'm not saying that happens with every random forest, so you got to keep that in mind. Technique 2 is upsample your minority class. For example, in this example, I only have, I don't know, 5,000 pixels of the minority class, but 500,000 pixels of the majority class. I just upsample my minority class to bring it up to 500,000. That's one option. The other option is downsample the this should be majority class. Okay, that's what happens when you copy and paste. Downsample the majority class, meaning you have 500,000, so only sample 10% of those, or even 1% of those, to bring them down to 5,000. Okay, and of course, technique number 4 is a combination of upsample and downsampling. Technique number 5 is penalize the learning algorithms. Again, for support vector machines and random forest, you can actually penalize it, and let's talk about that later on. I'm not going to explain everything in detail, but I'll show you how to do these things. Generate synthetic data. There are techniques called SMOTE, S-M-O-T, T-E, I think, and ADASYN. So I'll again briefly mention. And technique number 7 is, if you're using deep learning, add appropriate weights. Okay, I'll talk about all of these, and I'll let you figure it out on your own data sets. Now, before jumping in, like I mentioned already earlier, our pixel values 65 and 201, or labels 65 and 201 are the minority class, and the other labels are majority class in this example. Okay, so let's again, I covered this as part of my traditional segmentation. Please watch videos 67 and 67B. This is exactly what I did. Okay, I took the same code, and we are trying to do random forest based image segmentation using these two images. One is my ground truth, meaning my labeled image. The other one is the actual image. Okay, so let's go ahead and start reading our actual image, and I'll explain what I'm doing here just in case you haven't watched video 67. So we are reading an original image, converting that to grayscale, and reshaping it, of course, to put it in a data frame form. And then I'm adding the pixel values of our original image as feature number 1. We are actually generating features now, and then we'll train random forest on the features. That's the plan. Okay, so original image pixel values is my pixel feature number 1. So if I open my data frame, you should see that, okay, it contains original image, and then these are all the pixel values. Okay, so we have a lot of dark areas, so you'll see a lot of 0, and eventually you'll see a bunch of numbers later on. Okay, so that's the pixel value right there, and then let's generate a bunch of features. Now, the easiest way to generate a lot of features is using the Gabor kernel. Again, please watch my video on Gabor features. So it's just a convolutional filter where you can change sigma, lambda, gamma. So that's what I'm doing. I'm changing sigma, lambda, and gamma, and then it creates new filters by changing it. And let's go ahead and run these. And it's, if you can see the right-hand side, as you can see, each Gabor is different theta, different sigma, and different lambda. So after each one of these, the response is added to my data frame. So if you look up here, my data frame has, oh no, let's not open it. It's got way too many data points. And as you can see up here, we got 33 columns going from the original pixel value, Gabor 1, Gabor 2, and so on. So all we are doing so far is generating data so we can work with it, okay? Or generating features, I should say, from our base image. Okay, now I'm reading the labeled image, which is nothing but this image with pixel values encoded as 33 and so on. So let's go ahead and read that. And I'm also going to add this as my label, so it gets added as a label. So let's quickly look at the data frame head. So you can see we have, let me resize this. We have original image, Gabor 1, Gabor 2, Gabor 3, all the way, and the last column, sorry about this, let me resize this. And the last column is labels, and we have 33, 64, and so on. Okay. So where do we go from here? In fact, instead of mentioning that we have 3354, we can just type labels.unique, so it prints out all the unique values. So these are the 4 labels in our image: 33, 201, 231, 65. Now let's actually look at count how many labels of each we have. This tells us, you see 500, almost 490,000 of pixel value 33. Yeah, so what is our pixel value 33? Again, let's go back to our image, and pixel value 33 is this background. We have a lot of background, and the next one is pixel value 231, which is this grayish looking region. So of course we know that we have a lot of it. And then 201 is not bad. I have about 73,000 pixels of 201, which is the region that I am interested in, which is this region. Okay, that's 201. And the bright pixels, which is our pixel value of 65 in the label, we only have 16,000. So technically in your mind, we are like, okay, maybe pixel value of 65 is underrepresented, so it does a crappy job. But I think it does a good job because it can be easily separated from the rest. Okay, so let's continue here. I'll share the code, so don't worry about it. So now let's separate our data frame into X and Y so we can train our machine learning algorithm. So Y is nothing but our labels, right? And X is everything but our labels. So I'm dropping my labels column. Next, as usual, let's split our data into training and testing data sets. And I'm holding 20% of the data for testing and everything else, 80% for our training. Okay, here I'm including a few lines of code, but I commented it out in case you want to test out logistic regression or support vector machines. Now we are approaching our technique 1. What did I mention? The technique number 1 is pick a decision tree based approach. I'm not going to demonstrate that to you, but I have the code here. You can do it yourself. Both of those support vector machines and logistic regressions are very slow. So in the interest of time, I'm not doing it. So I'm directly jumping into random forest, and you'll find that random forest is definitely orders of magnitude better for this type of challenges. Okay, so let's define our random forest classifier. It's available as part of scikit-learn ensemble. And I'm only using 10 trees right now, number of estimators, but you can go up to 50 to see how it affects your quality, but that's not the goal right now. So let's go ahead and do that, and that part is fast. I just defined it. Now let's fit the model on our training data set. So this may take a few seconds, so I'll pause the video and continue. Okay, so 30 seconds later, it's done, and now that I have my model that I called model_RF, let's go ahead and predict it on our X test data set. So this is going to predict it on all the 20% of data that we held. So now let's start printing the metrics. Okay, accuracy. Now this is, if you look at some other videos on YouTube, one of the techniques they mention is using the right metrics, but I think that's not a technique to handle imbalanced data. That's something that you need to be prepared with, right? So accuracy, let's go ahead and prepare this accuracy, and then let's see how this looks like. So our accuracy is 94.8%. Amazing, we're done, right? I mean, this is great. We don't need to balance the data set. Fine. I'm recording this in the morning, otherwise I would have popped my wine bottle and we're done, right? But accuracy is not a great metric because it tells you the overall accuracy. And if our bulk of the data is oversampled and then the undersampled, we don't know how the undersampled regions are performing. So how do we look at that? Okay, first of all, let's look at our unique and counts. Let's go down here. Just remind ourselves that our pixel value 33 or label 33 has about 98,000. Well, this is the 80% of the total data, right? And our 65 has only 3,000 data points. 201 label has 13,000, not bad, and 231 has 88,000. Okay, so this is a quick reminder. Now let's print out confusion matrix. Again, I have a separate video for confusion matrix, so go ahead and watch it, but I'm importing that from scikit-learn metrics. And look at the confusion matrix. Now 96,180 correct identifications for whatever the first one, the pixel value 33. So out of 98,249, 96,000 are correct, 1,992 are labeled as, I don't know, something 201, and 77 are labeled as 231. Okay, and you can see that this one, these many, and finally it's 85,000 of these. So confusion matrix gives a good idea, visual idea, but I'm not very good at doing math just by looking at this. So let's go ahead and print the accuracy for each of these. So all I'm doing is taking this value and dividing that by the total number. Okay, that's pretty much it. And taking this value and dividing it by the total number of pixels. So let's print out the accuracy values per class. That's what I'm trying to do. So this is a great way of actually getting a good idea of how good it's performing. So for 33, 97.8%. Pixel value 65, remember, we do not have a lot of pixel value 65s, only 3,000. And yet it did a great job, 96.7%. That's because that pixel value, it's easy to segment it anyway. It's a bright, so it doesn't matter if it's underrepresented because the feature that represents that data is very strong. Okay, so even though it's underrepresented, you don't have to scale it up. Okay, so that's the reason why it did a great job there. Now pixel value 201, even though I have, for 201, we have 14,000 data points, much higher than the pixel value of 65 or label of 65, and yet it only gotten us 66% of accuracy. This is the challenge because this is a very difficult region to segment. We probably need additional feature descriptors, or we need additional data that comes from these type of features. So this is where balancing the data can be very important. Okay, so I hope we now understand the need for balancing the data, and finally 95.8% for this. Okay, now one other metric that's absolutely amazing is called ROCAUC score. So it's basically telling you the area on, again, watch my video on ROC and AUC. If you have older version of scikit-learn, it may not work because it usually ROC and is defined for binary classification, right? But in this case, we are looking at multiple. So we have 4 different classes. So if you have version 0.23 or later, then it works for multi-class. And still it does this binary one versus the others, but it gives a great score. Okay, so it gives the score. And the way you implement that is ROCAUC score, your y-test, and the second one needs to be probabilities. It's not your prediction. Normally when you do your, for example, when you do your, where is my accuracy? When you check your accuracy, you do the true values, which is our y-test values, and you do your prediction values as the next. In this case, the second one is not the prediction itself, but the probability. Okay, it may sound confusing, so I will include the link as part of this document. So go ahead and read more about how this thing actually works. Okay, and what type of approach you would like to use if it is a multi-class problem, and what are the labels. And our labels are 33, 65, 201, 231. Okay, so once I provide that, let's go ahead and run our ROCAUC, and we should see something around 90s, 97.4. Sounds great, but in relation to what? So let's try to balance our data and look at the same metrics. Okay, so far we did nothing when it comes to balancing. Well, we did one thing, which is picking random forest. Okay, and we checked out that it's already doing good. If you check, for example, support vector machines, that ROCAUC would be much lower, and these accuracies would be much lower. So by picking random forest, we already did a great job. Okay, so now let's go down to the second part of this. Now technique 2, what is it? Upsample the minority class. How do you do that? In scikit-learn utils, there is something called resample. Okay, go ahead and import resample. This helps us do both upscaling and rescaling, downscaling actually. Where is my downscaling? Downsampling. Okay, so resample. Okay, how do we resample it? Let me go up. Again, it looks like a lot of code, but there's a lot of repetition here. I could have been better in writing this, but anyway. So and now let's go ahead and print this value counts. Okay, we know this. Again, I want to remind that, okay, 33 and 231, we have about 500,000 data points. 201, 72,000, and 65, only 16,000. Okay. Now I'm actually separating this into, or splitting this data frame into 3 different data frames. Okay, one for the majority, one for the important class. It's not even under, well, it is a bit underrepresented, but this is the important class 201. This is the textured region I was talking about. And the other one, majority class. The majority class is the one with pixel values 33 and 231. And the one is the minority class 65. It's doing good, but I'm still calling it minority class. Okay, how do you upscale? Well, first let's upscale the minority, or upsample. Sorry, I keep saying upscale, but upsample. So I create a new data frame called minority upsampled, and then we call our resample method right here. And then the first one is df minority, right? I mean, this is what we want to upsample. And replace equals to true. I mean, it replaces sample. Again, please go ahead and read the documentation. And number of samples, 400,000. So how many do you want to create out of whatever we have? 400,000. The way it does that is it randomly selects a whole bunch and then copies them. Randomly selects the next time a whole bunch, copies them. That's how it's doing. It's not just taking this and then copying it. Eventually, you'll see that some are more copied more times and some are copied the less times. But this is a random process. Okay. And then I'm upscaling the important ones right now. Same thing, about 400,000. Exactly the same thing. And finally, I'm going to merge all the 3 channels, which is our df majority, the one that we just separated, the important upsampled, and the minority upsampled, all into one. So let's go ahead and run all of these and then print how many we have for each. It's pretty quick. I mean, the computation here is not that complicated. Okay, so now you see before is that, after is this. So now it is balanced. Okay, does it help? We'll see. That's our task next. So here it is. Run these lines. I like to run a couple of lines at a time, you see, because it's giving me some error, maybe because I didn't select the right lines there. Okay, but there must be an issue with the code somewhere. Okay, test 0. Oh, sorry, I didn't select all lines. Okay, so there you go. And then let's go ahead and train exactly using the same number of estimators. So let's go ahead and fit the model and go all the way up to here. So I'll pause the video again. This may take a few seconds. Okay, so this time it took a bit more time because we have more data. Okay, so let's organize this a bit so we can look at the result. Now, before looking at these accuracies, let's actually print out the ones from before, and so it's easy for us to compare. So let us go ahead and run these lines. This is for before, and now let's actually print the accuracy metrics after. So starting here all the way down to here. Okay, so let's compare this. Oh, I just realized it actually adds this code part here. Okay, so previously we got our accuracy to be 94.8, and now our accuracy is 97.7. So overall, it's a good improvement. Then let's actually look at the only thing that we care about is pixel 201 accuracy was 66% earlier, and right now it is 91.7%. So you can see the power of balancing your data. Definitely improved our accuracy for our 201 class. Now, if you look at the ROC AUC, previously we had 97.4%, and now we have 99.4%. Amazing, amazing, right? So just with upsampling, we seem to have solved this problem. In fact, let me give you, I mean, if you want to stop the video here, fine, you know. The best thing that works is upsampling, downsampling combination. Okay, upsample a little bit, downsample a little bit, and that combination works amazingly well. Okay, that's why I'm not going to show you the downsampling, but I just want to show you how to do this. So in this case, again, downsample, resample, we are going to resample it, and we are going to resample the majority, and number of samples is 30,000. The implementation is exactly the same as before, except here we are going from 400,000 something to 30,000 data points. Okay, that's pretty much it. And technique number 4 is both upsample and downsample. Okay, so far we learned, okay, technique number 0, collect more data if possible. Technique number 1 is use random forest, right? Technique number 2 is use upsampling. And we saw that they both really worked very well. Well, random forest, you can test it out with support vector machines. So technique number 3 was downsampling. Technique number 4 is both upsample and downsample. Now let's look at technique number 5, which is penalized learning algorithms. Again, I don't want to get into the details of what it means, but in summary, it's actually, I thought I added like some text here. It's actually penalizes, the downsampled or the minority class, any uncertainty or the mistakes in the minority class. It's good to learn. Again, Google search for penalized algorithms and see exactly what it does. Okay, and it increases the cost of classification mistake. That's pretty much it. Okay, on these minority classes. And how do we? I mean, it sounds like a fancy term, but how do we implement that? All you need to do is, as part of random forest classifier, just add class weight equals to balance, so it takes care of the balancing part. And this also works very well, actually. This is not available for logistic regression. I'm not sure if it is, but support vector machines, definitely you can write within, add this class weight equals to balanced, and it takes care of it. Again, please go ahead and test this out. I'm not gonna, again, waste your time by running it and showing you this. Now, technique number 6, I'm not sure how many of you are familiar with this. This is not, this is something we used to do in a synthetic way, like write code to do some extrapolation, interpolation of your data. But technique number 6, generating synthetic data, which is not copying or deleting data. It actually generates new synthetic data when you do upsampling. And there are 2 techniques, one called synthetic minority oversampling technique. The name says it all. And the other one is adaptive synthetic. I don't know which one is better than the other. Again, it depends on your specific application, but both are available. Now, what SMOTE is doing, actually, I gave a link so you can go ahead and see exactly how it works. And it's part of this package called Imblearn. So you will have to pip install Imblearn, and in there you'll find oversampling, and within there you can import SMOTE and ADASYN. And I'll show you an example of this. This will take a while, so I'll show you an example of SMOTE, SMOTE. So all you got to do is create an object for SMOTE and then fit it to your data. So I'm fitting it with my X and Y. So that's all I'm doing. And then once you create that, and then you can actually I'm splitting it into training and testing. That's all this is. Okay, so these are the 2 key lines there, and this is going to take quite a while. I think a couple of minutes on my system, very slow. Okay, and by the way SMOTE works, I think the easiest way to explain that is, let's say you have, in our case, we have 32 features, right? You have 32 features and the label. And for example, if you have the label 201 in our case, right? So it randomly picks like these 2 data points, okay, with the 201 labels, and then think of it as averaging all of these 32 features and then creating a new data point. Okay, so this is a quick summary of how SMOTE actually works. So now that it's done, let's go ahead and split the data set, the generated data, into training and testing data sets. This should be pretty quick. And before proceeding, I'm curious. Let's see how many data points before and after, right? So before, we know that we have 400 some thousand for our 33 and 231, and then 65 is so many. So let's actually run this other line so we can compare it. You should see 491,000 for everything. So all it does is it looks at, okay, what is the majority and what are the other ones, and then it kind of creates that many synthetic data points to match the maximum data point. So eventually now I have 491,532 data points for each of these classes. This is obviously very well balanced. So let's go ahead and run our random forest classifier and then look at the ROCAUC score. Okay, so there you go. So the accuracy is 96% and ROCAUC score is 98.6%. This is definitely better than not doing anything. meaning it's definitely better than working with imbalanced data, but not as good as the upsampled and or upscaled or downscaled or a mixture of those. Maybe this is just for this, image processing type of applications. Maybe it works better on, I don't know, financial data analysis or forecasting or something else. But so far, I've had very much luck, working with upsampling or upscaling, downscaling. I think we can call it downscaling or downsampling or upsampling. But anyway, I hope the message is conveyed. Now, this is our technique number 6. Technique number 7, if you're using deep learning, again, there are many other techniques, but let me just mention one technique that I typically use. I don't want to create another video for deep learning part, but for deep learning, one thing I usually do is add weights. Again, I'm doing exactly the same thing. I'm generating the same features, everything exactly the same, except instead of random forest, I'm using a very basic deep learning, which is a dense layer with 8 and then another dense with 4, because we have 4 outputs, right? And I'm using categorical cross entropy. But one thing I would like to show is, if I scroll this, metrics is accuracy. Okay, so now you can see, so this is my model. And then obviously deep learning is not as easy as regular machine learning in terms of handling data. So I converted my Y values into categorical. Okay, and I encoded the labels because my labels are 33, 201, 231, 65. So I first of all encoded them to 0, 1, 2, 3, and then converted them to categorical. Okay, again, please watch my videos on categorical. So I don't want to make this again a deep learning tutorial. Okay, so now to define the class weights, this is one thing I would like to really highlight. To define the class weights, you can do one of two things. In fact, let's not fit. Where does the fit come? Okay, let's actually run the code all the way until down here, so we have our data ready, because this may be important. So let me go ahead and run this. Hopefully it shouldn't take too long. This is pretty much the same we have done earlier. I just realized this is a different Python environment than the normal Python environment I work, because this one doesn't use GPU and this is 3.7 and so on. So because I think this is important, let me shut down this and then open Spider in a new environment and continue this tutorial. Okay, sorry about that. Okay, so this is our new environment. Again, going back to my Python 3.5, and we are where we left off. Okay, so again, just a quick reminder. So we have almost 450 to 500,000 for these two labels, 72,000, 16,000. Now, how do we add weights? You can add weights manually, or you can just get the weights computed. So here is automatically defining the classes. So from scikit-learn utilities, get class weight, and then within class weight import this compute class weight. And then how do you want to compute? Balanced. Okay, so you can also give a dictionary in this case, but let's just say balanced. Okay, again, look at the documentation, and let's go ahead and run these, and it should spit out. And let's go ahead and print class weights. I don't think I have. So it's mentioning that our class weights should be 0.51 for the first one, 15.49 for the second, 3.49 for the third, and 0.58 for the fourth. Okay, so these are the class weights, and it makes logical sense, right? I mean, for the first one, meaning it's talking about 33, right? Value 33, it says, okay, multiply by 0.5, meaning we are only taking half of them in a way. For the second one, class 65. Okay, so we have 16,000 data points. It says, okay, multiply that by 15, and the next one, multiply that by 3.5, which is this one, and the final one, multiply that by 0.58. That's exactly what that is. Now, if you already know the class weights, you can obviously, again, let's go ahead and print this, or you can actually give your class weights as manual, right? Either way. So in this case, the class weight says manual. I'm giving a dictionary, and by the way, I'm giving 0, 1, 2, 3 because we already encoded them. Okay, otherwise the values would be 33, 62, whatever. You know what I'm talking about. Okay, so let's go ahead and add these class weights. And once you define class weights, what do? When you are fitting the model, okay, you define your class weight right there. That's it. So this is one way of actually supplying class weights to balance your imbalance data during your deep learning exercise. Now, this has some effect, but this doesn't help all the time. So far, I haven't gotten amazing results on these type of data sets using deep learning. Maybe with a lot more data, I haven't done that type of testing. I'll let you guys explore that. But traditional machine learning worked great. Actually, sorry, let me take a step back. Instead of doing this, if you actually use the upsampling that I mentioned already as part of your data handling pre-processing before it goes into deep learning, it definitely helps. Okay, so in summary, there are many ways. Pick random forest if you're trying to use traditional machine learning. Do upsampling and downsampling. Okay, a combination that actually works very well. And SMOTE, explore that. And also penalized random forest also works fine. And don't forget about the class weights here. But then even if you're using this class, instead of using this class weights for deep learning, the traditional upscaling and downscaling also applies to this type of deep learning. Okay, I hope you found this tutorial to be obviously very long, but definitely useful. If you know of any other techniques that I haven't covered, because this is, you're limited by your creativity in terms of how to handle imbalanced data. If you have a trick that you have, please leave it in the comments so others can benefit from it. Thank you very much.